Hello. Today we are going to talk about converting different numbers to different bases. And to do this, we're going to use an important formula or concept called the Radix number system. Let's get started. What is the Radix number system exactly? Well, it is a method or a formula, a general formula, that allows you to convert numbers of different bases, including the numbers with floating point values. And here's the formula. If you let n be a radix number, which is any number in a specific base, then you can rewrite it into this form to convert it into a decimal value. How you would do that is you would take each individual digit of it, and then you would multiply it by the base with an exponent value at the top. And the exponent would be based on what placement the digit is in your number. And if you have a decimal number where you have floating points after the decimal on the right side of the decimal, then you would go backwards. You would be using exponents, negative exponents. To better understand this, we're going to give you a few examples. For example, here in binary, R would be 2. The base is 2. The two digits that you can use are 0 and 1. And that's why it's in base 2, because you only have two possible digits. An example number I have here is 1011 decimal 01. How would we convert that to decimal, for example? Well, if we use the formula we just talked about, you would have 1 times 2 to the power of 3, because it is in the third decimal place. And then you would have 0 times 2 to the power of 2, because it's in the second. Then 1 times 2 to the power of 1, and 1 times 2 to the power of 0. And then after the decimal point, you would have 0 times 2 to the power of negative 1, plus 1 times 2 to the negative 2. And if you calculate that out with a calculator, then you will continue to get this, which is 8 plus 0 plus 2 plus 1 plus 0 plus 0.25, which in decimal is 11.25. Now also I have a base 10 here around the number. A general way of telling people what the base is of the number you're looking at is to have a little number around it at the bottom of it, well, in brackets. So for example, on top here you see my binary number has a 2 on the bottom, and my new decimal number in base 10 has a 10 on the bottom. Okay, we'll try it again with octal numbers. In octal, the base is 8, which means that there are 8 possible digits we can use, which are from 0 to 7. Here's another example, 175.34. And if we use our formula again, in the same way we get 1 times 8 to the power 2, because 1 isn't in the second place, and 8 is the base, so that's why we use 8, plus 7 to the power, 7 times 8 to the power 1, plus 5 times 8 to the power 0, and so on. It's very similar to binary. And you can calculate that out yourself. Now here we have a decimal number that we are going to try in base 10. Our example here is 198.34. In decimal, there are 10 different digits we can use from 0 to 9, and this is the way that most people are familiar with. Now if we use our formula the same way that we did before, it would be done exactly the same as before, except that the base that we use is 10. And if we calculate all that out, you'll notice that we get the exact same number. That's because we are converting to decimal. So a decimal to a decimal is going to be the same answer. This was kind of pointless, but it's just to prove to you that this formula does work for all bases. Finally, the next most common base is hexadecimal, which is in base 16, which gives you digits from 0 to F. That means 0 to 9 plus A, B, C, D, E, and F. So here's an example number, 1AF.34 in hexadecimal. And if we put that into the formula, we get this 1 times 16 to the power 2 plus A times 16 to the power 1, and so on. And if you calculate that out, you get this statement, 256 plus 16A plus F. Now we have letters in this formula. What do we do with the letters? Well, you have to know what hexadecimal stands for, and to do that, it helps to look at the corresponding values of A to F for decimal in a table. Here's the table. Notice that from A to F, A will be equal to 10, F would be equal to 15, and all the other numbers would correspond in the same way. And also notice that from 0 to 9 in both decimal and hexadecimal, the values are the same. They do correspond to each other. Okay, so now that we know that, we can go back and substitute 10 for A and 15 for F. So we're going to have a little bit of additional multiplication in this statement, but it's not too hard. You should be able to finish this yourself. So let's summarize. We have 4 different bases that are commonly used that we looked at today. Binary is in base 2, octal is in base 8, decimal is in base 16. Decimal is in base 10. Hexadecimal is in base 16. Okay, now we showed how to change different numbers to decimal. How do we change from decimal to another base? Well, let's suppose we want to change this number 123.3752 to an octal number. You would divide by the base that you have. So in this case, we have the number 123 divided by 8, and we're going to get 15 with the remainder 3. We want to keep the remainder on the side because we're going to use that later, and we continue with the 15 to divide again by 8. And then we get a new remainder, which is 7, and then we take the 1 here and continue dividing by 8, which is 0, and we get a remainder 1, and then that's it. Now notice here I only did the one side of the decimal point. We still have the other side on the right side of the decimal, and we have to calculate that separately. Now if we multiply this time, we have to multiply when you're doing it on the right side of the decimal. Keep that in mind. So here we have 0.375 times 8, which is equal to exactly 3 there. We stop and we continue this until all the values after the dot on the right side of the dot are equal to 0. In this case, it looks like we're already done. But keep in mind that it won't always be this easy. You won't always just get 1 or 2 straight numbers. For example, if we were to change this number to 3.1, we would keep going. So we would have 0.1 times 8, which would get 0.8. So we would continue again. And again, we would keep going until all the values after on the right side of the dot are 0. Okay, if we go back to the initial question, we know that the right side of the decimal we got 3. So now how do we put all this together? Well, you have to make sure you do this correctly. If you don't, then you might have the reverse version of the number you want. For the main part on the left side of the decimal, you read from the bottom to the top. 173. But you would do the opposite for the fractional part. You would read from the top to the bottom, which would be 3, then 0, because there's nothing else. Okay, so therefore, if you put it all together, you would get 173.3 in octal. This form of converting is also called the remainder method, just so you know. There's another way to convert different numbers. Now keep in mind, we just did this for octal in base 8, but the process is exactly the same with other numbers. You just have to use a different base. For example, hexadecimal, you would use base 16 instead of 8, and binary you would use 2 instead of 8. Now there's a special way to convert from binary numbers to hexadecimal and octal bases, and also vice versa. It's actually a lot quicker than all the math that we've just been doing. Now here's a table showing all the different numbers. And notice, if you look in the binary column, and hexadecimal and octal, you might notice a pattern. If you looked in octal, which is the biggest single digit number you can have is 7. And that corresponds to the largest 3-digit number you can have in binary. Likewise, in hexadecimal, the largest single digit you can have is F, which corresponds to the largest 4-digit number you can have in binary. This is a special pattern, and it makes converting a lot easier. For example, if I want to convert this number, 10110110, from binary to hexadecimal and octal, well, this is what I would do. You would, in hexadecimal, you would take the binary number, you would split it up in groups of 4 digits. And then you would convert those individual digits to the corresponding value in the table that we just saw. And in octal, instead of grouping the digits into 4, you would group the digits into 3. Also, notice here, if there aren't enough digits to group everything into 3, you would start from right to left. And on the left side, you would just add 0 to the front if it's not a group of 3 on the left. And so here you go. If you have, if you convert this to hexadecimal, you would have B6. In octal, you would get 266. Okay, we just did a lot of converting, a lot of math. You might be asking, why? Why do we have to convert numbers like this? Why do we have different bases for stuff? We're used to using base 10 in decimal numbers. Why don't we just stick with that? Why in the world would we try any other types of numbers? Well, there are many different reasons and applications, but I'll give you the most obvious one to computer scientists. Think about computers. How are they made to store information? Do they magically store decimal numbers for everything? Do they have zeros, ones, nines, and twos and sevens and all that stored in the hardware? Well, no. They probably use binary. Well, I'm sure they use binary, and I'll explain why. For binary, you have only 2 possible values. And if you think of electricity, how many possible types of switches can you have for electricity? You can turn either on or off. That's 2 different values, which correspond directly to binary. Now, that explains why we use binary, but why the other bases? Well, consider this. Consider this decimal number, 19,341. If we convert that to binary, we would get, well, I'll let you do it, I'll give you a minute. Okay, so you would get this big number. Now that's a lot of digits, and okay, 19,341, that's kind of a large number in decimal, but it's not unheard of. That's reasonable to have to do some math with that. But this large binary number is kind of a pain to use and to read and to write out every time if we were writing all this on paper. So, and you can imagine if we had larger decimal numbers like 1 million or 2 million or a billion, how would that look in binary? Well, it would look like a huge pain to deal with. So how would we write this in an easier way such that we can write it on paper? Well, we would use hexadecimal or octal. If we did convert the number into hexadecimal or octal, we would get these numbers, which are considerably smaller and a lot easier to write on paper. Okay, I think we're done now. That's about how conversion works for different numbers of different bases. I hope you learned something today. Thanks for watching.